So let me refresh you guys as to what was done last class. This is just so that we can continue, you have some context for this lecture, okay? We'll just review last class so that you have a context of what we're going to do this lecture. So last class what we did was, we started looking at Laplace transform, right? So we have L of f of t is equal to f of x. And here f of t is a function of time f of s is function of s, which frequency or complex variable, right? And similarly we looked at inverse Laplace transform, L inverse of f of s is equal to f of t. Then we looked at partial fraction expansion. This is to aid inverse Laplace of complicated functions. Okay. And then we also looked at the context of differential equations and Laplace transform. Okay. This class, what we are going to do is we going to continue this discussion. We're going to introduce something called transfer function. Okay. by definition, the ratio of system output response to system input expressed as Laplace transform is called the system transfer function. Okay. Try to understand this because you'll be doing a lot of this transfer function business. The transfer function is, see, in this course and as aerospace engineers, a lot of time when you develop those mathematical models, whenever you use those laws, you're trying to find the input-output relationship. You're always that is what you want as aerospace engineers. You really are trying to figure out input-output relationships. And as control engineers, you're just trying to figure out how to get a desired output for a known input. Okay. So this transfer function is the ratio of system output. Output and response are synonymous. So we may use those interchangeably. System response means system output. The ratio of system output to system input is called the system transfer function. Okay? And if you look at the differential equations, you cannot separate out the input and output, correct? But when we take the Laplace of that, we can actually separate the system output and system input. And that is the reason we say it is expressed as Laplace transform. So this transfer function exists only for a Laplace transform of a system, or expressed as Laplace transform of a system. If you express the system as a differential equation, you cannot get a transfer function. Okay? So for example, you have find transfer function of the system dc of t dt plus 2c of t is equal to r of t. Right? So here c of t is the system response. R of t is the system input. Okay. Example? Right? This is how you're given this system, and if you're asked to find the transfer function, this is how you go about doing it. You take the Laplace on either side, okay? And then the Laplace of this is S into C of S. Laplace of this is 2 into C of S and equal to R of S. So look at this for a minute, for a moment here. C of t is the output expressed as a function of time. So when you take that Laplace, it just becomes output expressed as a function of S. C of t becomes C of S. If it's derivative, there is an S. If double derivative, there is S square. Okay. Now what you do is you can separate out C of S, right? C of S, S plus 2, and you have the ratio output to input. Okay. Once you have the transfer function, now a lot of you, many of you are what you're going to do is you're going to look at this and say you're going to compare the left hand side and the right hand side. Okay, left hand side, right hand side. You're going to say this is the output and this is the input. Don't do that. You're going to compare these ratios. Forget about this for a minute. You're going to say this is output, this is input. That is not the case. All right. So what is this? This itself is G of S. Okay. This whole thing is G of S. It is a system input-output relationship. Okay. The system response is denoted by this. The system input is denoted by this. We don't know what is yet we don't know what the input is. Okay. So regardless of what input is applied, the system input-output relationship is this. Okay. And if you take if you want it to be expressed in terms of time, you just take the inverse Laplace of that. Okay. Now what we are going to do is, since we have talked about system transfer function, from system transfer function, so TF means transfer function. What is system response? Okay. So you have G of S is equal to C of S over R of S, which implies C of S is equal to G of S into R of S. Okay. Now if R of S is given to be a unit step input, then C of S would be equal to G of S into 1 over S. Okay. How do you, so if R of S is given to be a unit step input, what that means is the Laplace transform. How is the unit step input? How did we define unit step input? 1, right? So the Laplace of 1 is 1 over S. Got it? So you remember this U of t is equal to 1 for t greater than 0, it is equal to 0 for t less than 0. So this becomes, when you take the Laplace of this, it becomes 1 over s. So C of s is equal to 1 over s into s plus 2. Okay. And C of t is equal to 1 over 2 minus 1 over 2 e to the power of minus 2t. Is this clear? Absolutely. Right. So just pay a moment's attention here. See, what you do generally, what you're used to until now was you were given this differential equation and you were asked to find a homogeneous and a particular solution, right? This is like the homogeneous solution. No initial conditions or all initial conditions equal to 0. And this is like the particular solution where the initial, what is the initial condition here? You're applied a step input. You're given, okay. So what we did here was we kept aside the differential equation solution. We said we'll look at this system. This system is essentially input-output relationship. We took the Laplace of that, okay, found the transfer function, right? And then we said, let's analyze this system for a step input, or let's find the unit step response. What is a unit step response? Unit step response is response to a unit step input. Response of a system to a unit step input is a unit step response. Right? You take this system, you apply step input to it, the response you're going to get out of that is unit step response. Okay? So what we did was we said we'll analyze this system, the output of this system or the response of this system for a unit step. And unit step means R of S is just 1 over S. Okay? So we said this is what we got, the Laplace of output. This is the Laplace of output. And if you split it, or if you do inverse Laplace on this one, if you do a partial fraction expansion and an inverse Laplace, you're going to get this. Okay? So this is the response. Unit step response of the system expressed as a function of time. Absolutely. Right. So if you look at this, this is a exponentially decaying function. You see exponentially decaying? Why is it exponentially decaying? Huh? You have this negative, right? So as t increases, it decays. Most of the natural systems are exponentially decaying systems. Okay? Let me not say that. Let me say this. Most of the systems which are stable are exponentially decaying systems. If it's an exponentially growing system, what happens? It says the system becomes unstable. Examples are, again, an atomic bomb is an exponentially unstable system. Have you ever experienced or have you looked at videos of buildings collapsing? Buildings they use sound to resonate the building and then make it collapse. Have you seen those? So if you, every object has a resonant frequency. What is resonant frequency? There is a natural frequency for every object, okay? And if you oscillate, or if you make that system vibrate at that frequency, it goes into resonance. It just becomes unstable. Okay, it will just start resonating, or it will just go into unstable mode. So what they do is, in this, if you want to collapse huge buildings, they'll just play sounds in that building. You know, if you want to demolish a building, if it is not it's not an economical thing to just go and hit it. So what they do is, they'll try to vibrate the building at different frequencies, and then once it hits resonance, it will start becoming unstable, and then everything will collapse. So that is an exponentially growing system. That decays. That is not a decaying system. That is an unstable system. Okay. So everybody is clear on this one? Transfer function and system response. No questions on this one? Would be a stable system, right? So the next thing we're going to discuss here is translational system transfer function. Okay. I've already told you we are going to discuss a lot about spring mass damper system. Okay, because we can design and build or emulate any system, any physical system using these three components. So when you're talking about translational system transfer function, we look at three basic entities, or three basic elements. Okay. The first one spring, and we'll use this to represent the spring. So the spring constant is K. The displacement is denoted by X of T. The input force is denoted by F of T. So for this, the input-output relationship is simply F of T is equal to K into X of T. Okay. And there's one more quantity we'll introduce. We'll call it Can somebody take, I'd like somebody to take pictures and post it on Blackboard for everybody. Okay. If you have taken it, try to put it up on Blackboard. All right. Can you do that? All right. So we'll introduce something called this one. You have taken this is okay. Got it, Sammy? Welcome. So we'll introduce a term called impedance, okay? And the impedance of a spring is just K, where K is the spring constant, all right? The second element or the second entity is a damper. The damping coefficient is denoted by F of V, as is used in the textbook. The displacement is denoted by X of T. So the input-output relationship you have F of T is equal to and the impedance is denoted by, which is FV into S. Okay. And the final element is a mass input-output relationship is F of T is equal to M d square X of T over dt. MS square. Okay. Huh? Right. It is just a Laplace. So think about it like this. So what is this impedance? In here, what is the input? Huh? Time is not an input. Time cannot be an input. Huh? The force, F of T. What is the output? X of T, the displacement. So the output is not really predefined. It doesn't have to be predefined, okay? For example, you might be interested in velocity, and one of your colleagues might be interested in position or just the displacement, or somebody might be interested in acceleration. Here we are interested in displacement. Okay, so the output is displacement and the input is a force, applied force. So the input-output relationship is applied force is equal to K into x of t. This K is a constant. You understand that, right? Spring constant. It is a property of the material and how you coil it. Okay. Now, what is if you take the Laplace of this, you're going to get f of s is equal to K into x of s. Right? So when you look at impedance, just look at, don't look at output over input, look at input over output. It is K, just K. Right? Right. Just put output over here. It's resistance to what is happening. Okay. So it is K, Laplace. If you do that to, this is again the relationship between, for a damper, force is equal to applied forces, the damping coefficient into the velocity. Okay. Now again, if you take Laplace, you're going to get f of s equal to f of v into s into x of s. Right? If you just ignore if you take input over output, the impedance, it is Fv of s. Got it? And similarly, this is for the mass. All right. This input-output relationship, how did we get this input-output relationship? How do we get any input-output relationship? I just told you. No. The laws. The laws are which will give you laws of physics. So here you are applying actually Newton's laws. Okay. So this is Newton's second law essentially. Or you just do apply some laws of statics. Input-output relationship. So laws is what gives you the input-output relationship. So what do we do with this? We'll take a look at an example. Okay. So if you have a very simple example, you have a spring, you have a damper, okay, and you have a mass attached to. So this is Fv, K, and M, and you have an applied force. And this is your displacement. All right. So this is a simple system. Now you'll be asked, the question would be, find the transfer function G of s. Okay. So what you do is you start with you can start with Newton's second law. Okay. What is this point? You know what this point is? What does this mean, arrow? Direction of force is all given there. Vertical, yeah. The initial position, when no force is applied, this is where it is. From that point onwards, the displacement, since the force applied is in that direction, the displacement is also, we are assuming the displacement is in that direction. It just means that, okay. This is the point of equilibrium. When no force is applied, this is where this mass is, okay. Now, input-output relationship. Or we'll use Newton's second law, okay? So what does Newton's second law say? Applied forces is equal to change in momentum, or mass into acceleration, not velocity. So we are assuming an LTI system, right? We talked about LTI system, remember? Linear time invariant system. That means the mass of this system is not going to vary as time progresses. So that is the reason we can use this mass into acceleration. Otherwise, change in momentum would be, linear change in momentum, rate of change of momentum would be mass into acceleration plus velocity into change of mass. So that velocity into change of mass goes to 0 because mass is not changing. Okay. Now, if you look at this, tell me if this makes sense. F of t minus kx of t minus Fv x dot of t. So x dot of t is what? Just this. Dx by dt is x dot of t. That's what we're going to use. Okay. Is equal to mass into, let me start with dx over dt, m d square x of t over dt square. Now, you should have asked me a question. Okay, let me first ask you guys a question. Do you agree with this? Right. I'll get to that. See, when you apply this force like this, what happens to the spring? Spring tries to push it on the other side, right? So that is this force. So we are assuming this direction to be positive. So the spring force is in this direction. The damper will also do that. So if you try to push the damper, whatever direction you are trying to push, it will try to push the other way. So that is, and the force is actually, it's proportional to, the force is proportional to Fv to dx by dt. Okay. So this is the left hand side, and this is the right hand side, mass into acceleration. Now, one of the things you need to notice here is, we ignore the masses of the spring and damper. That is the reason we just have this m. Otherwise, it has to be the whole system. Okay, that is, you should ask such questions. What happened to the mass of the other system? Because in comparison to this mass, we assume the spring and damper are really negligible, so we just ignore that. Okay. Yes, Keith, what's up? When you actually talk about so if you're, this together can make a system, right? That time when you want high fidelity models, you will not ignore the mass of this. So you'll just add the mass of that. You'll actually measure it and see. Include that mass. So we add it to the right side. So you look at it as the entire thing is accelerating in that direction. Okay. There's a force component and then there's an acceleration component. Right. These are the force components are pretty significant, but the acceleration component of these two is insignificant. We assume it is insignificant. Okay. So this is what you have for now. To answer Melvin's question, this is what you get, Melvin. This is what you're used to. You're used to m d square x of t over dt plus kx plus fv dx of t dt, or mx double dot, right? This is what you're used to, plus kx plus fv x dot. Remember this, you must have come across this quite a bit, right, in your dynamics courses. So this is how you get that mx double dot plus kx plus fv x dot. Okay. This means these are functions of time. Okay. X dot double dot means it's a function of time. Double derivative of x of t. Derivative with respect to time. X dot and x double dot, the dot and double dots for any variable apply only to time derivatives, correct? You are aware of that. Okay. So that's what you get. Now, if you take the Laplace of this, what are you going to get? Taking Laplace transform, we're going to get f of s equal to m s square x of s plus k x of s plus fv s x of s. X of s ms square plus, I'll just move this, fvs plus k is equal to f of s. Therefore, transfer function g of s is equal to g of s is equal to you've arrived at the transfer function. So let me just note here that C of S is the general notation for any input. Here the any output. C of S is the general notation for any output or response. But here specifically the output or the response is this displacement x of t or x of s. So you have x of s, the input, general notation for any input is r of s. But since here it is f of s, we do that. Now, what is the response? If I say find the unit step response, so in exam, this is how you're going to get. You're going to get like 6 points for finding the transfer function and 2 points for finding the unit step response. 2 points you're going to get for only one line, for writing only one line. So what is the unit step response here? Unit step response, unit step input. Unit step response means response to unit step input. Unit step input f of s is what? 1 over s. It is 1 in time domain, 1 over s in frequency domain or Laplace transform. Okay, so f of s is 1 over s. It just means f of s is 1 over s. So all you have to do is x of s is equal to g of s into f of s, right? Or x of s is equal to 1, that is g of s over s. You just need to give me this line. If I say unit step response, if you just give me this, you will get your 2 points. Okay, just 1 over s. Multiply the system transfer function by 1 over s for a unit step response. I think we'll stop here.